nice Monday morning here. I'm Wendy Crandy, and today I'm going to be talking to you about student-driven machine learning projects in Python. So since this is PyHC, I'm going to be specifically focusing on heliophysics-related projects that are relevant to this community. I'll introduce the topic, and then I'm going to hand it over to Laura Sandoval, who has served as a mentor to students on machine learning projects, and Allison Liu, who is one of my current students. And they're going to dive into a lot more details here. So just to give you a quick outline of what I'm going to be talking about, I'll start by giving you a little bit of background about myself and my student team, and then I'll give you some examples of challenges that we've run into, and maybe some prospective solutions for how the community can help out for newcomers who are coming into this field without very much knowledge, especially students. So a little bit about me, if you don't know me, although I think a lot of you do. I have a PhD in astrophysics from ASU, and I did a postdoc in computational chemistry at NIST. I also did an Insight Data Science Fellowship in 2017, right before I moved over to LASP. And since I've been at LASP, I've really been interested in the intersection of science and data science. So I like to work on scientific questions, but I like to use cutting edge solutions to do it. I'm also interested in the intersection of art and technology and human experience. So this is a picture of me and my husband at opening day for Meow Wolf Denver. And if you haven't gone, I highly recommend it. It's a really cool exhibit.
I'm jealous.
Okay. Yeah, so part of the machine learning work that I do involves training students in applying data science techniques to space weather and heliophysics projects. So I'm involved with this in two ways. One way is that I am the leader of the Space Weather Trek Deep Learning Lab. And part of our mission is to provide machine learning resources to students so that they can succeed at applying these cutting edge technologies to space weather projects. I'm also the co-PI and the coordinator for the Boulder Solar Alliance Research Experience for Undergraduates program. And this last year, I did a lot of work to incorporate machine learning methodology, coursework, and sub-cohort meetings into the program so that the students had a community on their machine learning projects. The current team who is working with me are Allison and Erica. They are both undergraduate researchers at CU Boulder, and you're going to hear from Allison later. Allison's been working with me since the spring, and Erica just joined within the last month. They are part of a larger group of students who work on these machine learning projects within kind of the space weather heliophysics realm. And I also show the previous students who have contributed to this. They're a mix of CU students and REU students. And the primary project that they've been working on is a solar flare prediction project. So I'll talk a little bit more about that in a second. So the first question is why we use Python for student machine learning projects. The primary reason is that it's open source. They don't have to pay for it, which is really important when you're working with students. There's also a lot of community support, and this community is part of that, but also the larger Python community where you can say, go check Stack Overflow to see if this question is already answered. That's a huge benefit when you're working on student projects. It's also intuitive for both beginning programmers and more advanced programmers. And there are built-in machine learning tools like scikit-learn, PyTorch, Keras, and some of the tools that are built by this community help with heliophysics projects as well. However, there are some areas for improvement. And the first question that I want to pose to you is what challenges do you think that newcomers face getting started with machine learning projects in heliophysics? So you can go to this link, polev.com/wendycrandy735 and answer this question, and the results will start populating on the screen. So I'll give that a second. And Laura put the link in the chat too. Data wrangling, understanding, yes, that is a big part of it. Lots of wrangling data. Packages, use, setup, environments. Yeah, so I think that we are seeing a lot of this converge around data understanding, data wrangling, preparation, packages, environment, tools, all of that. So Laura, can you take a screenshot of this for me real quick?
Yes, just did.
All right, thank you. All right, so yes, you are all correct in the things that you are saying here. So I'm going to give a couple of examples now from projects that I've worked with students on to give you some ideas of some specific challenges that we've run into. And a lot of these are related to some of the things that you've already put up on the screen. So the first is the solar flare prediction project. So for this project, our goal is to predict whether a type M or greater solar flare will happen in the next 24 hours. And the solar flares are classified by their peak flux range. So I've outlined where M and X are on this diagram. And those are the most likely to be tied to problems here on Earth, which is why we're targeting them. And we're using magnetogram line of sight images from SDO HMI. And each of the data points that we have has a vector of calculated space weather quantities such as magnetic flux, and those are called sharps. So this is the data that we're working with. And the very first blocker that we always run into, and I hear this from lots of students, is they have trouble figuring out how to get the data, how to pre-process the data. So they read papers that say, go to JSOC, and then, here are all of these pre-processing steps. And it's not always immediately obvious how to access the tools. So sometimes those tools are available to make that process easier, but it's not always immediately obvious how they're supposed to access those tools. And I think Allison is going to talk more about that later. Okay, so when we're working on this project, the model that we used was called an LSTM, a long short-term memory network. And we used that because it captures time trends in the data. So it's particularly applicable to time series data. And let's see, it just skipped a slide. But the first blocker that we ran into with the LSTM is that hyperparameter tuning is really clunky and time consuming. So the hyperparameters are all of those little things that you change in the LSTM. So there are a number of layers that you have to change. And changing all of these things takes a lot of time. It's not always obvious where you're supposed to start. So that entire process is really time consuming. It would be really great if there was an easier way to do it. And then the way that we evaluate that model is using something called true skill score. We use the true skill score instead of some of the more traditional metrics like accuracy, because it works well for unbalanced data sets. So when you're working with solar flare data, there are a lot more non-flaring times than flaring times. Therefore, the data set is very imbalanced. And this is a good scoring metric for that type of data set. So for the true skill score here, the student wrote his own scoring function. So this was another blocker. There's a lack of extensive built-in scoring metrics. So it's really easy to find something like an F1 score or an accuracy or a precision or a recall. But if you're looking for something more specialized to the fields that you're in, that's really something that you have to write yourself. So that's another blocker that we ran into on this project. And then Allison is going to talk a lot more about the data augmentation side of this. But essentially what we were trying to do is augment the SDO data with SOHO data. And the main thing that we ran into when we were trying to do this problem is that it was hard to visualize the overlap of the data. So we wanted to know when SDO and SOHO overlapped in time and had matching times. And we also wanted to know what the quality of the data looked like over time. And both of those things, we needed visualization tools to be able to do. And then finally, for the solar flare prediction project, we don't just want to know what the model is doing, but we also want to know why it's doing it. So a student named Cody Feldhaus worked on an explainable AI project in Lyme this past summer. He used the same magnetogram data and he used the Sharps features and some features from past research. And for his prediction model, he used a support vector machine. And the goal was to see which of the features were the most important for explaining a single prediction. So that's a single time flare or no flare in the next 24 hours. And this is what Lyme outputs. So does this look intuitive to you? Like if you're just looking at this, do you immediately understand what it's telling you? I know most of you are muted or turned off, but to me, this is not at all intuitive. So there are a bunch of numbers here. The feature names are cut off. It's not really clear what it's telling me. So the last blocker that I have here is that we really need a better and more intuitive way to do explainable AI. Because if it's that weird and clunky, then it's not really explainable, right? That's the entire point, is that you're supposed to be able to explain what you're seeing, and those unintuitive visualizations make it really difficult. So a couple of the solutions that I think could be addressed here, and HelioPy has already addressed some of these. Simple data download and visualization. So that addresses that first blocker that we were talking about. Some standardized and well-documented pre-processing routines, so AI-ready data. Visualization tools that show where two time series data overlap. Better explainable AI tools, ones that have better visualizations. Intelligent automated hyperparameter searches. So if you're trying to pick the number of layers in your LSTM, how to do that more intelligently, and comprehensive built-in scoring metrics that are relevant to the field that we're in. So finally, I'll just leave this question open to you. So again, if you could go to Poll Everywhere and put in your responses here. What do you think that the HelioPy community can do to support, here I say outsiders, people who are new to the field? So new researchers, students, and as you respond, it'll start populating on the screen. Jupyter Notebook sharing, yes, definitely. Documentation, absolutely. Big documentation, yes. Let's see, Panhelio, tutorials, examples. Yeah, so we're kind of converging on a few answers here. Tutorials, documentation, Jupyter notebooks, training examples, all of these things are really important. Laura, could you take a quick screenshot?
Okay, done.
Thank you. All right, so yes, those are all very good ideas. And you're going to hear more about some of these ideas from both Laura and Allison, who I'm going to hand it over to now. We can do some comments and questions at the end, but if you have anything quick and specific for me right now, I'm happy to answer.
Sean just said he didn't know HelioPy did hyperparameter searching, and I didn't know that either. So that was.
Yeah, I want to talk about that at some point. Maybe this might be a little bit early.
Yeah, okay, we can have some discussion at the end, but for the sake of time, I'll hand it over to Laura now.
Okay. Okay, so this is my outline. I'm just going to give a little bit of background about myself. I've had a couple of personal examples for where I've had barriers when working with data, and so I wanted to describe those. And then I've heard, you know, often in the machine learning community, some common obstacles, so I'll go over those, and then so that'll be it. I am a software engineer at LASP, and I have been for the past 5 years. I do a number of things. I started off doing some instrument calibration for the SIM instruments on the Source and TESIS satellites. I'm a data manager for the WAVE project. I am a lead of the Atlassian transition team, and then I'm just starting on the Libra project as well. I've had some machine learning experience while I've been at LASP, but none before. And mostly it's involved coming up with the ideas on my own and researching some machine learning techniques I could use, mostly really the statistical machine learning techniques, no neural networks. And then I've participated in the NASA working group where we've written some papers and discussed ideas about machine learning. So I'm still relatively new to the field, but these are my mentees that I had for my machine learning projects. The first two, one was actually an undergraduate student and one was a high school student who was very advanced. And so I did a little bit of research and came up with an idea to automate the Macintosh classification. And the Macintosh classification is basically, you have researchers that hand notate images of the sun every day in order to try to predict solar flares. And so the things that they look at are the penumbra, the sunspot distribution, the umbra, like different things that you see in an image. And so what we wanted to do was to automate that and make it less subjective. So we use the SDO, HMI, magnetogram and intensitygram data, and then also use the machine learning techniques of k-nearest neighbor, random forest, and SVM, and AdaBoost. And the work was pretty good. It resulted in a flare prediction at about the same accuracy as performed manually. The second machine learning project that I worked on was with Ashley Lieber, and she's shown upper left. And so we used multiple linear regression, another statistical model that predicted the total solar irradiance using solar features that you would find in the SDO data, and also we did some image processing. And so, the thing is in each case, the largest barrier for each of these projects was simply downloading the data and doing the image processing. So that I would estimate it took about 4 weeks or so to get the students started. have them find the place to download, do the image processing, understand what was happening. And by that time, you know, a third of the, or almost half of the program had passed. So the program for REU students is 10 weeks. So I thought, well, I think I thought I could show you an example of, you know, what an ordinary person would go through, like that has not worked with the SEO HMI data a lot, to download the data. You go through a number of pages trying to figure out the best way to download the data. You know, you can manually download it. You can put specific items in that you want. You have to register. That's another unclear thing. And then finally you come to this website where it says, okay, there's a Python module called DRMS that you can use to download the data. And that's really the best method. So I was like, great, this is exactly what I want. I have the documentation here, I have the tutorials, and everything is more straightforward from here on. But for a student, this might be daunting, especially a student that is just now learning Python. Maybe they had some other, you know, experience in programming like IDL or something like that. But if you're just learning Python and you're getting familiar with it, then this is a little bit more challenging to figure out. And also the image processing, there's a lot of, I think SEO HMI data is more progressive in that it has a lot of metadata, it has a lot of information about active regions, but it doesn't have everything. So here is an example of what Megan Smith had done. She had to figure out what the area of the umbra is. So that's like that dark region of the sunspot. And then she had to figure out, you know, what the area of the penumbra was, what were the north-south distance of them, east-west, the symmetry, the range in pixel brightness, that type of thing. And some of the active region information was available through the SGO data, but a lot of it wasn't. And it makes me think, has this been done before? Or it seems like we must not be the first people to do this, but we looked and there was no like example code or tutorials out there. So we ended up doing the image processing from scratch. So anyways, at that point, you know, we were probably midway or a little bit past midway through the project, and then we could actually start to do the machine learning, which was more interesting for the students. So anyways, I've noticed that just talking in the NASA working group that the data preparation and downloading and that type of thing are really the most important phase of the machine learning project. And it consumes about 80% in general of each person's time. So accessible machine learning data sets are highly valuable for the community. And an organized code repo with tutorials and examples for various data sets would also be very valuable. So that's what I found from my experiences mentoring the students and participating in the working group. And one thing I wanted to show was something that I found very useful, and I think a lot of people have, is this website. This is the Stanford HMI Science Nuggets website. And a lot of the work that Monica Brobra produces, she always includes at the bottom the example Python code. And I found that that was also very valuable. So some takeaways is that I feel like the field probably needs some leadership, documentation, organization in order to improve data accessibility. Organized repos with examples would be very valuable. Machine learning ready data and also descriptive metadata. I think that, you know, Wendy pretty much touched on all of these too, and I think Allison will say the same thing in a different way maybe. So that's been my experience. So any questions? Okay, I will let Allison take it over then. Let's see.
Okay, can you guys see my screen?
Yep.
Yep.
Yes.
Okay, awesome. So my name is Allison. I am currently a senior at CU Boulder, and I'm studying applied math and computer science. So I'm really interested in using computational tools to solve research problems, and particularly research problems that can't be solved without a computer. So very similar to Wendy, actually. And I am so that naturally lends itself to doing machine learning and data science. So I've taken a lot of programming classes and a lot of machine learning classes. And I started out in physics, but I have a little bit less of the science background and more of the computer science background. But nonetheless, I am new to doing Python in heliophysics. But I have done I have done multiple machine learning projects. And I am also very interested in machine learning ethics and empowering underrepresented students in STEM. Okay, so currently I am working with Wendy at LASP and with the Deep Learning Lab to do solar flare prediction. And so right now my project involves using machine learning to create a cohesive magnetogram dataset. So Laura was talking about how having a machine learning ready data set is very valuable. And so that's sort of what my project is aiming to create right now. But so there's essentially two data sets, two magnetogram data sets that are used for solar flare prediction, SDO-MDI and SOHO-MDI and SDO-HMI. And essentially the two data sets are incompatible, mostly due to resolution, but also things like rotation angle and things like that. So my project is trying to integrate them. And so with any machine learning project, my first step is to download the data and pre-process. And then I want to try multiple machine learning algorithms once I have the data downloaded in order to upsample the lower quality data set and to matching the higher quality data set. And step 3 is data analysis. And then hopefully being able to use this cohesive data set to improve solar flare prediction. So I guess Laura was talking about the difficulty of downloading data and for students. And so we're gonna go on a little journey to download data. So, when I first started, I was like, okay, how am I supposed to get my data? So, resourceful computer science student, I was like, okay, I'll just Google downloading SOHO MDI data. That makes sense. So, I was like, okay, I'll just, this link looks pretty legitimate. We'll go there. Okay, so I'm brought to this page, and this is the MDI historic archive page. And so I was like, okay, the data isn't served from this page, so I'll just go to this JSOC link, which ends up taking me to this page. Okay, so we're here, and I have a pretty good idea at this point of what sort of data that I want, I think. And I know that I want the HMI and MDI magnetograms. And so we'll focus on MDI. So I'll click on the MDI dataset link. Oh, and I'm right back here. So this is back to the historic archive page. So I guess I'll just click on the JSOC link again and we go back. So now we got to try something new. I guess I'm going to go with this MDI data products was my next guess. And I went through all this again while I was preparing this talk, and I was just like, but okay, so we go to MDI data products, and it sort of expands, and I want to click that one. Okay, so now I'm here, and we have a list of all these MDI data set links. There's full disk and high resolution, and I sort of was not, like, I sort of knew that I wanted the full disk ones, but I wasn't sure what the difference was. So I ended up going into this like sort of many hour long sort of research expedition trying to figure out what these data sets actually meant. And I think what I ended up finding was that the high resolution ones just ended up at a different focal length, and sort of the focus of them was slightly different. And also, I still am not sure which of these two magnetogram data sets to use. Even now, I'm not sure what the difference between the 96-minute version and the regular version is. But I was like, I'll just pick one. So I went with that one. Okay, and then I'm brought to this page. And this is the JSOC database export tool. And you kind of see these dates and you're like, okay, I can sort of figure out how to export this date range that I want. And you end up just like typing it in like this and putting in all the dates, like the date range. And there's very specific other like formatting things you can do. So you can say, I want to filter these 96-minute cadence, minute cadence magnetograms and filter them by 250 or 288 minutes and just space them out a bit more. But that took a little while to figure out. And you end up just getting to this website that exports data to an HTML link if you download enough. And so you have this thing that says record and file name, and you end up getting, well, when you download more than one file, you get a big list of these file names. And each of these file names is a FITS file, and you have to click on each one to download individually from this HTML link, which obviously I was like, this is horrible, and there's a better way to do this. So eventually, like Laura was saying, if you click on this getting access or data access link and go to the FAQ, finally this little link right here that's very, very important shows up, and it's sort of buried within this FAQ. And this Python module is the module that allows you to download all of the data through Python and export it as a zip file or export it as a folder of FITS files, which is what anybody would want in the first place anyways. And so it was just sort of like a very chaotic experience. And I think, a big question is, how much of this experience is part of doing data science and important for a student to experience? Because if you take a machine learning class, you get all the data anyways. But how much of it is really important to experience and like have the frustration of, and how much of it is actually valuable to a student's learning experience, particularly if they only have like 10 weeks. And I'm fortunate to have more than that, but even then it's just like, I think that data downloading is one of those things that is very frustrating and not something that students who are trying to learn get a lot out of. But I think it seems like, in talking about this, Wendy and Laura and I sort of all had this similar experience of getting data. Okay, so, and then I was sort of reading through the mission of PyHC and why PyHC was created while I was creating this talk. So I guess I'm going to go through just the important, the major things that were sort of values of and reasons for creating PyHC, and sort of like the non-underlined words that sort of stood out to me and that were important to me. And so centralization was one of these things, and having all of the data in a cohesive place, in a centralized place, like heliopython.org, I think is very helpful. And accessibility was also another one of these reasons. And so the words that sort of stood out to me were licensing and open source. So I think it's very good that, the mission of PyHC is that this software is open source for everyone to use, and that the fact that licensing is very secured. But I noticed that visibility, ease of use, and approachability for new users were sort of missing from that mission statement. And those are sort of things that I wanted to add. I think visibility, like I sort of demonstrated in that example of downloading data, it's very not intuitive and it's not very easy to find the resources that are available. And it's very confusing, and it's very confusing for new users to figure out, and it's very time consuming. And so not only is it frustrating, it actually is not the best use of resources to have everybody who's trying to download data sort of go through this experience. Attribution, having citations and collaboration and credit for the software that's created. Rigor, creating accurate and reliable scientific analysis tools. And finally, best coding practices. So this is definitely an interdisciplinary problem. And sorry, this is a lot of text, but this is sort of a quote that came out of the paper from 2018. If it is good enough to produce reliable scientific results, it is both good enough for pure consumption and of interest to the scientific community. However, good coding practices improve both adaptation by others and reproducibility. And this quote sort of rubbed me the wrong way, like particularly the first part. And I think, but the point of this is that we want to create code and software that's sustainable. And I argue that purely working code is not enough. And that's often like something that is in science that is not sort of taken seriously enough, because I think a lot of scientists just try to get purely working code. But code that isn't rigorous or well documented, especially for public use, hinders collaboration and the improvement of software and research progress itself. And so it is very, very important that we have this documentation and we have this use case documented, and that we have tutorials for people to use, because science is so collaborative. And so for the benefit of new users, maintaining well-documented code and creating things like new packages, tutorials, and Jupyter notebooks is very, very important. And I also think that creating things like data downloading and pre-processing packages specifically, and making these things visible. And so this is sort of a side question I had that I don't really have an answer to, but also like I personally, just having worked on a couple open source projects myself, is that, how do we support this development of this open source software when it takes a lot of time to develop and create, and not necessarily at the benefit of the researcher, because you don't, creating, code that works for everybody and documenting it doesn't necessarily benefit somebody's own research. So that was sort of a side question that I just sort of had the thought. But specifically, since we're focusing on new researchers, just having that documentation and having people who are motivated to create this documentation. And then, sorry, finally, I switched sides a little bit really. This was sort of something that I found while I was researching, was that something that could possibly be turned into a Python package or a PyHC package, but this was a package, this was a paper that publishes a method for preparing, for doing data pre-processing and throwing out a lot of unimportant data for the SOHO and SDO data sets. And I plan on using this, or trying to, in my future research in the coming weeks. So takeaways, I think that accessibility is one of those things that is often just sort of used as a blanket word, but I think specifically with PyHC, ease of use, visibility, and promotion are things that need to be improved and focused on. And with that can be advertising. And then creating things like code examples, tutorial notebooks, and ML-ready data sets for students to use. And then also sort of bridging this gap between research programming and computer science. And I think that involves a lot of interdisciplinary work between computer scientists and computer scientists who are interested in research. And that's all I have. Thank you.
I held off on talking about the comments because I didn't want to interrupt, but I think everybody related to what you said with the walkthrough. I have an echo going on here, so I'm sorry about that. Let's see. It says classic Helio scientists doubling and tripling as data engineers.